But let's continue to our third speaker, Professor Karl Vernet, Vice Dean for International Affairs from Technical University of Liberec. Karl, it's nice to see you. It's nice to see you via the internet. I hope that we will meet, maybe in Tel Aviv. I didn't see you for a long time, so maybe we'll be in Tel Aviv. So Karl will speak about one of the main, the heat storage. He will speak about heat storage by the separation of silica gel.
So, thank you very much. I hope that you can see now my presentation.
Yes, we can see it and we can hear you. It's quite okay.
Okay, thank you very much once again. So I'm coming from the Czech Republic, and I decided today to speak about our, I would like to say, results relating to the absorption of the energy or the storage of the energy. And we decided to use the sorption process because we have already several experiences in the field of the research. And I will be talking now about previous results and the new results. First of all, my area of the research, it's the area of the energy. And we are looking at the different kind of the problem. The goal is the same. That means to save the energy. And we mostly are focusing on the energy transfer, energy efficiency. We look as well at the technology which are used in the smart buildings and mostly connected with the energy storage. And of course, the one part of our research is focused as well on the smart materials and the material research, because a lot of, I would like to say, properties and the processes we can are just connected to the material research. So it's as well the part of our interest. First of all, what is generally the method which we use? So I will be mostly talking about the experiment and the CFD. The experiment, because I'm coming from the field of the thermodynamics and the fluid mechanics. So at the one side, we design the equipments in which we can just confirm or study some processes in order to understand in details. And secondly, in order to maybe improve the facility or operating conditions. For those part of the experiment, we use a lot of measurements like the PIV, hot fire anemometry, and so on in order to identify the velocity field, in order to identify the temperature field, and how I said, to understand the background about the flow features and thermodynamics processes. As another part of our research, it's concentrated on the theoretical research, which is represented by the CFD, computational fluid dynamics. And for the calculation, we use the 3 different type of the computational codes. That means everybody maybe knows the ANSYS, which is mostly very preferred in the students' work and diploma work and so on. Then I myself, I prefer to use the OpenFOAM, which has a lot of advantages. One of the most advantages that we have a source code, so we can extend this code to programming the parts which we needed to study. And in the past, I was working a long time on to develop the own computational code, which has a name, the VM or finite element method for 3D. And it's fully parallelized, used for the incompressible flow simulation. The advantage, the most advantage of the own code is, of course, that we can completely control our computational processes inside. So this is the technology which we use, or the techniques which we use to carry out our research. And I would like to mention it at the beginning. And now I go slowly to the topic of our research. So the one of the topics is just the sorption process, which we used for the thermal storage. And we are just at the beginning. So our task or the goals today, it's to construct the facility using which we'll be able to demonstrate the feasibility of these techniques. And we are studying the material properties in order to reveal under which operating conditions we are able to effectively store the energy. If I tell you at the beginning some main aspect or the main facts about this kind of the heat storage, of course, everybody, we are talking about the heat storage. We can imagine the sensible storage tanks or the latent storage tank, which are commonly used. And with this technology, we have a lot of knowledges. On the other hand, it's possible to use the sorption process, which is relatively new. And using the sorption process, we can practically store and after that release more energy per kilogram of the materials, which is used as with the, for example, sensible heat storage. And we have as well no problem with the change of the volume, which is the critical point for the latent heat storage system. And what is as well advantage that you can store a long time this heat without the heat losses. That means it looks like so, it looks funny because at the one side we store the heat, on the other hand, we have no problem with the heat losses, which I think it's just fascinating to carry out such kind of the research and to use this technology in the future for the heat storage system. So the main task today is to develop the facility, which is possible and which is possible to carry out the experiment and to respond to questions. Which material is the best for the heat storage using the sorption process? Secondly, under which conditions we can use the maximal effectiveness of the storage system, and in general, to, I would like to say, identified the best sorption process efficiency for the future facility. Before I start to speak about the particular results, I would like to mention it here, the previous results. This is what you can see. It's now the work from our student, PhD student. He has already finished the PhD study, and he started to research the sorption process for the CO2 capture, and as well using the sorption process. That means we use here the temperature to accumulate or to store the CO2 and again the release. And the system, it's control only the value of the temperature. Above, you can see just the experiment, which is very simple experiment. And inside, you will find the active coil. And using the temperature, we can actually capture the store or the release, or the capture the CO2 or release CO2. And this temperature swing adsorption techniques, it's as well used later for the heat storage. So below, you will see the graphs here. And the graphs locate just or indicate the change of the temperature regarding to the change of the concentration. Not only the experiment, it's just the way how to just study this problem, but as well we carry out the numerics. Numerics, it's just not easy to do it. In this case, we use the open form, and we look inside how this sorption process is working. And it could help us to understand how I said the backgrounds of the sorption process. The basic question is the effectiveness of the sorption process for the CO2 storage, and just the numerics and experiment. We carry out the both to just extend the experimental results by the numerical or the theoretical results. How I said to find the appropriate or to design the appropriate system which can store a lot of CO2 for relatively small amount of the materials. There are two slides which demonstrated the previous research. Actually, 5 years ago, we started this process or the study of the sorption process used for the CO2 storage. Today, we are going in direction to heat storage, but the sorption process and all the knowledge which we have already founded here, we can use furthermore. And now you can see some overview about the possibility to store the energy. And it is the liquid absorption, solid absorption process. we can use as well some kind of the chemical reaction and the composite materials. If you look now on this problem, we are going in direction to use the silica gel. This is the solid adsorption, and the silica gel is the first one using together with water. And the second one, it's cellulite, which is mostly the second option to use this material for the heat storage. What is the difference for us? Especially, it's the fact that the silica gel can work for a lower temperature field. So it's better for the experiment because we don't have to just heat up the air to so high temperature level. And secondly, the silica gel, it's very easy to have and or to purchase, and some material properties are well known. So this is the reason we decided at the first step to use the silica gel, and we have found the relatively excellent experiences. This is the first concept of the equipment which was just constructed or the design and constructed later for the experiment. And here in the container, which is indicated by the letter C, you will find just the silica gel material, which is homogeneously distributed. And we can change the different type of the mode. That means we just can dry up the material inside, or which is used to just to store the energy, or we use the, to release the energy, we use the second step. That means we mixture the air with the humidity, with the moisture in order to start the chemical reaction. During this, we can release the energy again. How it's working exactly, I can just describe here. That means there are two steps which are in the cycle. That means they are repeating each other. And the first one, which is called like the adsorption or the discharging, that means we have just the energy which is already stored in the sorption tube. And we deliver the moist air, which start the reaction inside, and practically the material can capture this moist. And as a result, at the output, you will find the hot air. On the opposite, if this sorption tube is already empty, we start the second step, during which we can actually charge this sorption tube again. That means we deliver only the hot air. We are calling about, or we are talking about the drying process. As a result, you will find the air and the water together with the lower temperature. And during this process, we can actually store the energy. And now if you create a cycle and you will repeat these two processes, so we can just discharge and charge the energy, and all it's about the time and about the frequency. Of course, the problem is that any materials can degrade during this process. And this is as well our topics of the research, and I can show you some results. So first of all, this is the amount of the mass absorbed, or the water or the humid absorbed in the material. If we just compare the kilogram of the vapor divided by the total amount of the absorbent. And as you can see it on these graphs, it describes the amount of the absorbed moisture regarding to the time. And very important, it's the first 20-30 minutes in which we can absorb a lot of vapor into the materials, and the less the change is not so drastically to see. And what you can see as well, we have performed this test for several cycles. It's relatively time consuming because the first type of the experiment, it's not fully optimized. So it's a little bit difficult to perform a lot of cycles, but definitely from these results, we can see the degradation, or the effect of the degradation of the material on the ability to capture the vapor into the materials. It is just the one first step which we partially describe furthermore in this publication, which you can see below. This degradation of the capacity of the ability to materials, the materials to capture the energy can be described if we look at the specific power, which is again described as a watt per kilogram of the absorbent which is used. And you can see as well the mean specific power, which is just demonstrated on this graphics on the right side. In the both case, we could demonstrate that after some specific cycle, the material just lose the ability to work properly. Of course, there is a trick that you can do the regeneration of the materials and you start the materials once again from the excellent condition at the beginning, but this is sometimes the problem. How I said, the previous experiment has or had the one big disadvantage that it was not fully optimized. So it was not possible to carry out more than 5-6 cycles because it was time consuming. So we decided to construct the new facility, which will be fully optimized, and we can just run this experiment a long time to observe what can happen with these materials after many cycles. And this second, the second experimental device, it's very similar to this, which you could see before. Instead of the hot air, we are now use the fan, which use the heating of the air at the appropriate temperature. In our case, we are talking about the silica gel. For drying process, for the charging process, we use the temperature field about 20 to 70 degrees. And for the discharging process, we are talking about the 30, 35 degrees. So the temperature, how I said at the beginning, in the case of the silica gel, it's not so high. So we can, without any danger, to work with this hot air. And we can construct this experiment device. And now it's still under construction. We have already the first results, but we are still working on to fully optimize the process. That means during the night, we can significantly change or we can be able to change the cycles in order to just find the appropriate materials properties. So this is the conclusion, some summarize of our testing, which you could see now, that not only the first test, but as well the progress in the design of the second experiment. And of course, not only the silica gel is interesting, the zeolite materials is another materials which is very popular today to use for this purpose of the energy storage. And we are just thinking about to use this material as well in the future, but it requires the higher temperature for the heat storage. So this is all from my side. Thank you very much for your attention.
Thank you, Carl. Very, very interesting. You were talking about 70 degrees. What were the temperatures?
Yes, the temperature was up to 70 degrees for the silica gel. That means if you charging the energy, that means if we are dry up this absorbent in the container, we use the temperature between 50 to 70. And of course, the temperature can just influence the process itself. That means it is as well the part of our research. So we know that the material is working between this temperature field between 50 and 70, which is as well recommended by the producer of the silica gel. And for the discharging process, for the discharging process, we use the lower temperature. It's about 30 degrees.
So if you have some kind of residual heat, you can store it in some kind of silica gel.
Exactly. This is just the excellent for this temperature field. It's excellent conditions. We had two ideas how we can actually practically use this technology. The first one, it's the combination with the solar power. It means instead of the water, we can use the air. We can actually heat up the air in the solar panel. And this heated air, which can reach just about 100 degrees of the Celsius, if we are not talking about the concentrated solar power, it's excellent as an input temperature for such kind of the facility. And we can, for example, store a lot of the energy inside of the silica gel and can be used, for example, later during the night to release the energy. This is just one practical application, which is already possible to see today.
Yeah, thank you. Very interesting. I can see Non is asking about, did you consider the effect of high-low pressures?
Oh, very good questions. So the temperature is the one thing, the temperature, the pressure, it's another problem of the sorption. Of course, we can use the temperature to control the cycle. We can use the pressure. Today, we are working only with the pressure practically under condition of the atmospheric pressure. So our study just a little bit ignore the effect of the pressure on the sorption process. But theoretically, this question is correct because the pressure can influence the sorption process itself, but it's not the objective of our study.
Okay, thank you. And I will mention that some of our students will come to your laboratory to work on this work, and it's very nice. I hope that